Now we discuss yet another question from the section Differential Equations. This question has appeared in Joint Entrance Examination Main held on 20th July 2021 in the morning shift. The question is from the section Differential Equations. The question is, let y is equal to y of x be the solution of the differential equation x tan of y by x dy is equal to, in brackets, y tan of y by x minus x into dx, valid in -1 less than or equal to x less than or equal to 1 under the initial condition y at x is equal to half is equal to pi by 6. Then the area of the region bounded by the curves x is equal to 0, the ordinate, x is equal to 1 by root 2, the ordinate, and the curve y is equal to yx, which is the solution of the differential equation, in the upper half plane is, the area is given to be the four options here. So you have to find, first of all, consider this differential equation and find its solution subject to this given initial condition, and after getting that particular solution you have to find the area of the region bounded by the curves x is equal to 0. X is equal to 0 is the ordinate, that is y-axis. X is equal to 1 by root 2, another ordinate, and bounded by the curve y is equal to yx in the upper half plane. Agreed. So the options are given. The areas is how much? That is the question. We discuss the solution. This question is little lengthier, but however, I will try to explain all the details of the solution. We have the differential equation x is equal to tan of y by x dy is equal to, in brackets, y times tan y by x minus x dx, in the valid in -1 less than or equal to x less than or equal to 1, and under the initial condition y at x is equal to half is equal to pi by 6. Now it may be written as, we will take this x to the other side, that is x is multiplied here, the other side it will divide, then it will be y by x minus x by x is minus 1, so that will be equal to tan y by x, and dy differential dx differential now becomes derivative dy by dx is equal to y by x tan y by x minus 1. This is the differential equation. Now we will now find the solution of the differential equation. We have the differential equation. Call this equation as the 1. So it is a first order and first degree differential equation, and it's also called homogeneous differential equation. And for homogeneous differential equation, the method is put y is equal to vx, where v is a function of x, then dy by dx is equal to v plus x times dv by dx, and the equation now becomes tan y by x will be tan v into dy by dx is v plus x dv by dx is equal to v tan v minus 1. Tan v multiplied by v plus x dv by dx is equal to v tan v minus 1. Now tan v tan v V tan V cancels, and you are left with x tan V dv by dx is equal to -1. We separate the variables. Tan V dv is equal to minus 1 by x dx. Variables are separated, and this method is called the variables separables method. Now integrate. Integral of tan V dv is equal to minus 1 by x dx plus ln c. Integral of tan V is ln log of secant V, and integral of 1 by x dx is log of x minus log of x plus ln c. So this will be equal to ln secant V is equal to ln c by x, and this will give you secant V is equal to c by x. This is the solution, and this solution has one arbitrary constant, and this is the general solution. The general solution of the given differential equation 1 is secant y by x, v is y by x is equal to c by x. Now you want to evaluate this arbitrary constant c, where c is the constant of integration. Now that c is to be evaluated. So to find c, we use the given initial condition. What is the given initial condition? Y when x is equal to half is equal to pi by 6. That means y is pi by 6 when x is equal to half. We will use this condition and evaluate the arbitrary constant c. So secant of y pi by 6 by x 1 by 2 is equal to c by x is 1 by 2. So this will imply secant pi by 3 is equal to 2c. Secant pi by 3 is 2 is equal to 2c. 2 cancels, and we will get c is equal to 1. So thus we get a particular solution. The particular solution is secant y by x is equal to 1 by x. Invert it, then you will get cos of y by x is equal to x, and take the inverse on both sides. Y by x is equal to cos inverse x. This implies y is equal to x cos inverse x is the particular solution of this differential equation. This differential equation is solved, and we have obtained a general solution. Used the initial conditions, we got a particular solution. The particular solution is y is equal to x cos inverse x. This is the curve now. So we have to take this curve and find out the area as is asked. The required particular solution is this: y is equal to x cos inverse x. The area capital A of the region bounded by the curves x is equal to 0, x is equal to 1 by root 2, and the particular solution y is equal to y of x in the upper half plane is what's the formula? Is equal to integral 0 to 1 by root 2 y dx, and integral 0 to 1 by root 2 y is x cos inverse x dx. Now, what is the integral of x cos inverse x? That's again a different problem. So that I will show you how to integrate that and get the integral of that function in a separate slide, and I'll come back to this once again after that. We'll now find integral x cos inverse x dx. After finding out the integral, we will talk about the limits later. Integral x cos inverse x dx. This is equal to integral u dv, where u is cos inverse x and dv is x dx. So when dv is x dx, v will be integral x dx, that is equal to x square by 2. When u is equal to cos inverse x, du is equal to minus 1 by under the square root of 1 minus x square. So we are going to apply what is called the integration by parts. So that is equal to integral integral u dv is equal to uv minus integral v du. This is by integration by parts. And what is u? U is cos inverse x, v is x square by 2 minus integral v x square by 2 to du minus 1 by root of 1 minus x square. That we have simply substituted here. So now that will be equal to this first term is as it is, but this is equal to minus 1 by 2, this 1 by 2 taken out, integral of minus x square by under the square root of 1 minus x square dx. I call this as the I. So you will get the first term minus 1 by 2 I, where I is this integral. So again, how to evaluate this integral is the question. That I'll show you in the snippet beside. I is equal to integral minus x square by under the square root of 1 minus x square dx. Now add and subtract 1 in the numerator. That is integral 1 minus x square minus 1 by under the square root of 1 minus x square dx. So we will separate 1 minus x square by root of 1 minus x square. That will be equal to root of 1 minus x square dx minus integral 1 by root of 1 minus x square dx. To evaluate this, I remember a formula. That is, the formula is integral under the square root of a square minus x square. If you know the formula, put it. Otherwise, you also do it. Put x is equal to sine theta and go on doing it also. You can do that. And for this, I will recall this formula: integral under the square root of a square minus x square dx is equal to x by 2 under the square root of a square minus x square plus a square by 2 sine inverse x by a. So in this, a is equal to 1, you substitute, you will get integral under the square root of 1 minus x square dx. So that will be equal to x by 2 under the square root of 1 minus x square plus 1 by 2 into sine inverse x minus integral of 1 by root of 1 minus x square dx is sine inverse x. So half sine inverse x minus sine inverse x will be minus half sine inverse x. The first term is x by 2 under the square root of 1 minus x under the square root of 1 minus x square. So the I value is x by 2 under the square root of 1 minus x square minus 1 by 2 sine inverse x. The I value we have obtained here. We will come back. We'll come back here and substitute. So that is equal to the first term 1 by 2 into I. The I is this. This we have written in the red. And now simplify. X square by 2 cos inverse x, 1 by 2 into x by 2 minus x by 4 under the square root of 1 minus x square minus 1 by 2 into minus 1 by 2 plus 1 by 4 sine inverse x. So we have got the integral. So the integral x cos inverse x dx is equal to x square by 2 cos inverse x minus x by 4 under the square root of 1 minus x square plus 1 by 4 sine inverse x. So now we'll go back and we are at the computing the required area. The area capital A of the region bounded by the curves x is equal to 0, x is equal to 1 by root 2 and y is equal to y of x in the upper half plane is capital A is equal to integral 0 to 1 by root 2 y dx is equal to integral 0 to 1 by root 2 x cos inverse x dx. This was up to this we have done it, and we went on to find what is the integral of that, and the integral of that is integral x cos inverse x dx is equal to x square by 2 cos inverse x minus x by 4 under the square root of 1 minus x square plus 1 by 4 sine inverse x. That we substitute here, and to be evaluated between the limits 0 to 1 by root 2. So x is equal to 1 by root 2, substitute here. So 1 by 2 into x square. X square is 1 by 2 because x is equal to 1 by root 2. Cos inverse 1 by root 2, that is pi by 4, minus 1 by 4 into x is 1 by root 2, and root of 1 minus x square is equal to root of 1 minus 1 by 2, that is 1 by root 2 again, plus 1 by 4 into sine inverse 1 by root 2. So that will be this one. And for cos inverse 1 by root 2, sin inverse 1 by root 2, we write down the pi by 4, and we get 1 by 4 pi by 4 minus 1 by 8 plus 1 by 4 pi by 4. That's equal to, the first one is pi by 16 minus 1 by 8 plus pi by 16. Pi by 16 plus pi by 16 is pi by 8 minus 1 by 8. Take 1 by 8 common, and that will be 1 by 8 in brackets pi minus 1. So that's your answer, final answer, final answer. The question, and the question is a very big one, and sometimes now and then such questions do come in the exam. And what is the option? So let's look for the options. The options are given 1, 2, 3, 4, and our answer 1 by 8 into pi minus 1 appears against the option 1. So therefore our answer is option 1. Thus we have come to the end of the discussion of the example that has appeared in a JEE examination. I hope that you have understood the solution and go on, practicing more problems of this type. I wish you all the best. Good luck. Thank you.